In this problem, we have the opportunity to look at the relationship between a spring constant, a diameter, and a length of a bar with respect to the elastic modulus that we're trying to calculate of the material that makes up the bar. So let's start by writing out what the spring constant is. Let's also include the diameter as 1.1 centimeters. And we'll also include the length, or 15, which is 15 centimeters. At this point, we've written all the numbers, all the parameters that have been given to us, and we're still in the search for what is the elastic modulus. Let's turn to some of the equations we've discussed in class. One is a form of Hooke's law, relating the force and the displacement to each other through a spring constant, K. And we have a spring constant given as 134 kilonewtons per millimeter. Another is Hooke's law, but the form that relates the stress to the strain through an elastic modulus, E, which is something that we do want here. Now, using just these two equations, it's not clear how we can relate what we've been given to what we want. So let's go a little bit further. We can figure out that a stress, sigma, is equal to force over area. Now, it may not be clear why we want to talk about force and area because there is not a force given, okay? But this is an expression that can prove useful when we do some substitutions. And then the final expression that we're going to bring in from our understanding of mechanics is the relationship between strain and displacement and its original length, or the original length of a bar. So let's go ahead and do some substituting. We have F over A is equal to sigma, so we can plug that in. And we have E times epsilon, and epsilon is equal to delta over L, so we can plug those together. We go a little bit further, and we have a relationship for the force and K and delta. So we put those together, and we rewrite the right-hand sign that we already had. We realize that there are deltas on both sides of this equation, so we can cancel them out and rewrite this equality as we find here, and rearranging things such that we can get E, the elastic modulus, we multiply both sides by L. And this is the expression. The elastic modulus is going to be the spring constant K times the length of the bar divided by the bar's cross-sectional area. We can then write out the expression E with the parameters that we've been given, K, L. And A, we didn't write out what A really is, but we know that if this is a cylindrical or circular cross section, it's a cylinder, then we can say that it's going to be pi d squared over 4. So let's go ahead and show how we can calculate the numeric value using Google and using Colab or Python. So we go over to a web browser, and if we recall, let's see if we can recall, we have that 134, and you already see that I've done this problem before, so it's going to come out like we see here, and this is going to be pi times, we got to do that in parentheses because there's a unit there that makes it easier, squared, and then divide by 4, and we get the following. We get a result in pascals. That's a good sign because elastic modulus has the same units as stress. And the question was actually asking for us to have the elastic modulus in gigapascals. So let's go ahead and write in GPa like that. And we get around 212 gigapascals. And if you recall, the elastic modulus of steel is approximately 200 or 210 gigapascals. So whoever was writing this problem probably was thinking that the material in question would be steel. Now let's go ahead and work this problem using Python. So we can open up a new script or notebook in Google Drive, and we'll do import numpy as np, control enter, go ahead and start another line of code. This might be a little, let's shrink it down just a little bit. All right, and we have K is going to be equal to 134 kilonewtons per millimeter. Now, when using Colab to run these types of calculations that have units, it's often a pretty good idea to go to the base units of the metric system. So let's go ahead and do that. So we know that 1,000 newtons are going to be equal to 1 kilonewton. So we'll go ahead and say, okay, now we're in newtons. And we're going to say, oh, 1,000 millimeters are equal to 1 meter. And so we can do that and as well. And we'll get that this expression for K will be in newtons per meter. The length is 15 centimeters. Well, once again, we probably don't want to keep it in centimeters. We'll go ahead and keep it in meters, like so. And the area is going to need to be defined through a diameter. So I could define it straight up like that, but I could also put in diameter like this, and it's 1.1 centimeters. But again, probably a good idea to convert to meters. And then we can write the expression pretty quickly for area. So we have pi times d squared over 4. And the elastic modulus, if we look below, right there, it's KL over A. So E is equal to K times L divided by A. And we'll go ahead and print it out. So we have print E equals, and we'll do np dot round of E, which we've calculated, and we'll say to 1 decimal place. And if we do this, this will give us the answer in pascals, but we want it in gigapascals. So we're going to go ahead and put a G there, and we're going to multiply by 1 e to the minus 9, right, like this. We run this, and what do we get? 212 gigapascals. And there we have it. That's the answer. Thank you for watching, and I hope you found this information useful.